In this video, we're going to take a look here now at the third law of thermodynamics. And the definition of this is that the entropy of a pure crystalline substance at absolute zero, so at 0 K, 0 Kelvin, is equal to zero. So we see that written in the form of an equation right there. So let's look at some entropy changes when we talk about chemical reactions. So standard entropies, by definition, these will be the molar entropy values of substances in their standard state. So whether something in its standard state is gas, that just means at standard normal temperature and pressure, right? So at 298 Kelvin, specifically at that temperature, the reference temperature, we usually see hydrogen in the form of gas, nitrogen gas, oxygen and gas. But we can increase entropies when we increase molar mass, or we found rather that molar entropies tend to increase with molar mass. So let's take a look here at this chart, and we can see if this was a single substance and at 0 Kelvin here up to whatever this point is, we have a solid. And then we can see that isothermal process here indicated where we don't have an increase in temperature because this is our temperature shown here on the x-axis. Then when we're in the liquid phase, we can raise the temperature of this substance, and we see all the while that entropy is increasing, which correlates with an increase in temperature. So if we look over here on the right at this table, 19.1, we can see the standard molar entropies of some selected substances. Once again, entropy is given in this unit, joule Kelvin. Specifically when they're molar entropies, we're going to say joules per mole Kelvin. So these are some of the values that you see associated with these molecules in gas phase and liquid phase and solid phase. We should also note that due to that equation up here, that we will always have a positive entropy value. It can never be zero or less than zero. Because once again, these are measured at values above 0 Kelvin, and therefore we will always have some entropy. Let's take a look at some values here for some molecules, and the more complex the molecule is, the greater its entropy. So we can see methane here, the simplest of the three structures, has an entropy of 186.3 joules per mole Kelvin. This is the shape, right? We can see just 4 bonds here. And now we have ethane. So now we have 2 carbon atoms and a total of 1, 2, 3, 4, 5, 6, 7 bonds. All of those can have their own vibrational modes. And then we have the largest molecule here of the 3 propane, 3 carbon atoms bonded, and then we have 8 hydrogen atoms also bonded. So many more bonds, many more vibrational modes, and the highest entropy of any of the 3 compounds here. So there's an equation that we'll use a little later on, and we see that the change in entropy can be calculated for chemical reactions by a similar method to when we did enthalpy calculations in Chem 1, where we take the sum of the reactants with their coefficient in front, the entropy change of products minus our entropy of our reactants, and we can find our change in entropy for the reaction. And don't forget, both N and M here are going to be the stoichiometric coefficients from the balanced chemical equation. So in the next video, we'll take a look at the next sample exercise.